we will generalize now the idea of linear independence for any vector space. So we know this idea for the particular case of the Euclidean spaces Rn, but now we're going to see how do we generalize this for any vector space. And we are going to say that a set of vectors in a vector space B, and remember that now when we say vectors means any element in the vector space. I mean, doesn't mean necessarily a familiar vector in R3 or R2. Can be, for instance, a vector can be a polynomial, or a vector can be a matrix. That depends on what vector space we are talking about. So any element in the vector space is going to be called just vector. So a set of vectors in the vector space is linearly independent if none of its elements is a linear combination of the others, and otherwise is linearly dependent. To say that none is a linear combination of the others is the same thing as saying that when we do a linear combination and we equal to 0, this linear combination has only the trivial solution, because if it has any other solution other than the trivial one, so if we can put here 3, 4, 1, whatever numbers there that are not 0, 0, 0, 0, so then what will happen is that one of them, just solving for it, can be written as a combination of the others. So that's why this condition is then equivalent to say that a set of vectors is linearly independent. So essentially that's all what we need to do with this set of vectors to figure out if they are independent. So we do a linear combination, we equal to 0, and remember that this 0 here is the 0 vector, but the vector in whatever vector space we are. So for instance, if it's the vector space of the polynomials, that would be the 0 polynomial. I mean the polynomial that has all coefficients equal to 0. If it's the space of matrices, would be the matrix 0, the one that has all the entries equal to 0. So that will be then the 0 on the vector space, whatever vector space is. So for instance, let's consider this set of polynomials, and let's see if this set is linearly independent or not. So let's consider the polynomial 2 minus 2x, 1 plus 3x minus x squared, and the polynomial 5 plus 3x minus 2x squared. So we have here three polynomials that belong to P2, and we want to study if they are linearly independent or not. That's the question. Is this set of vectors linearly independent? And remember that vectors mean now these three polynomials. Okay, so in order to decide if it's linearly independent, we need to make a combination of them that give us the 0 and check if the only solution is the trivial or not. So let's do the combination. That will be certain number, scalar, times the first one, another number, times the second one, plus another number times the last one. And this should be equal to the 0 polynomial, which is 0 plus 0x plus 0x squared. This is the 0 in P2, right? So this is the 0 vector. Okay, so now we do the operations and we consider the identity of these polynomials. So let's do distributive here. We have here 2a. So once that we do all the distributive here to do this operation, now we are going to group like terms. So let's start with the numbers. So we have here 2a, b, and 5c. So let's put those together. 2a plus b plus 5c. It's everything that doesn't have x, right? Plus. And now I go for all the things that have an x. So just x to the power 1 will be this one, and this one. So that will be, and so that will be minus b minus 2c x squared. And that should be equal to the polynomial 0 plus 0x plus 0x squared. Now, for these two polynomials to be identical, this one has to be equal to 0, this one has to be equal to 0, and this one has to be equal to 0. So that will give us a system of equations. And now the question is, does this system has a unique solution or have infinitely many solutions? Remember that a system equal to 0, we know that it's always going to have at least a trivial solution, but what we want to know if this is the only one or there are more than that. So for that, we can, for instance, we can do, at this point, we can do several things, right? One of the things that you can do is to calculate the reduced form of this system. Here you have already the 0 here, you can see here easily the subtraction of these two. So I'm going to copy the first one as it is, and the second one will be then 4b plus 8c, and the last one as it is, 5/2c equals 0. And so here we can leave just b plus 2c equals 0, and here 0 equals 0. Okay, so we have an echelon here, and we can see then from here already that this system has infinitely many solutions. So we can deduce that the set of vectors that we have here is linearly dependent, right? So then this vector is not Li, which is the same thing that said that is LD. Alternatively, instead of doing the reduced form here, we could just have calculated the determinant here, right? So we know that in order to have a unique solution, I mean only the trivial solution, the determinant had to be different from 0, right? So we could have just calculated this determinant 215 minus 2, 3, I mean just copying the coefficients here, right? 3, 3, and 0, minus 1, minus 2, and this determinant, you could see that this determinant is equal to 0. And so that would be another way to say directly is LD. Because in order to be Li, it have to be different from 0. Okay, so two alternative ways to do it. Either you calculate the echelon or you calculate the determinant, but you can then decide if three polynomials then are linearly independent or not. And then we knew already what means in a vector space to span the space, as we saw in the previous lesson. And so putting these two things together, so if a set of vectors span the set B and are linearly independent, so then they are going to be a basis for the vector space. And the cardinality of a basis is the dimension of the space. All the bases have the same number of vectors, and that is going to be the dimension of the space. And a particular result that sometimes is useful in practice, if a vector space have dimension n, so then n linearly independent vectors are always a basis. So in case that the number is n, I mean in case that the number of linearly independent vectors that you have is n, I mean is the dimension of the space, so then you can say that it's a basis, I mean without having to prove the second condition. I mean if they are n, so then that guarantee the spanning part. Particular bases, so we knew already the standard basis for Rn, right? So in Rn, if you consider the vectors 1 and everything else 0, right? And you are moving the 1 like to the second and everything else 0, and so until the last one that have a 1 there. So this is the standard unit vector basis for Rn. In particular for R3, we know that these three vectors are the standard bases, right? The vectors that we call I, J, K. So that's something to have in mind, to have it as a reference to the analogy with the new vector spaces that we are learning now. So for instance, for the vector spaces of the polynomials of degree n, a basis is going to be given, the standard basis is going to be given by the vector 1, the polynomial 1, the vector x, which is the polynomial x, the vector x squared, x cubed, all the way until xn. So this is the standard basis for Pn. Observe how many vectors are here. 1, 2, 3, 4, n plus 1. So see that if you count carefully, you will see that the number of elements here is n plus 1. So the dimension of Pn is n plus 1. So for instance, the vector space P2, the vector space of the polynomials of degree less or equal than 2, has bases then 1, x squared. So in particular, 3 elements in the base, right? So that means that the dimension of P2 is 3. Okay, so this is an important basis then of the set of polynomials of degree less or equal than n. Meaning that any polynomial then can be written as a combination, linear combination of these polynomials here. And you can see also what are the coordinates, right? Having in mind the I, J, K and the coordinates of any vector in relation to I, J, K, you can see what are the coordinates of each polynomial in function of this base. In the matrices, same thing. So if we have a matrix of any dimensions m, and so a standard basis is going to put a 1 in the first entry and everything else 0. Everything else. And so then you are moving the 1. So you will put 0, 1, everything else 0, 0, 0, everything 0. And so on until the last one. So you can see that there are many matrices here, right? So you can count how many. So we could see that in this basis here, there are m times n matrices. So for instance, if we consider the matrix 2 by 3, so what will be the basis here? Well, be 1, 2 rows, and 3 columns. I complete everything with 0, right? That's the first one in the basis. But you see all the ones that they have to still write, right? 0, 1. So this set is the basis of this. In particular, you see that there are 6 matrices there, right? 2 times 3. So that's the dimension of this space. So the dimension of the space of matrices is actually m times n. And so we can consider, as we know in the space of vectors, we can consider the coordinates of a vector relative to the standard base. S is going to be the standard base. In R3, if we have a vector that is 3, 1, 2, so the coordinates themselves here are the coordinates in the standard base, right? Because this is 3 times I plus 1 times j plus 2 times k. So whatever coordinates we have written like this, those are the coordinates in the standard base. So what about the polynomials? So for instance, let's consider P2. So P2, whose standard basis is the set 1x squared. So if I have the polynomial, let's say 4 plus 2x plus 5x squared, and it's good, and you should write the polynomials in this order. Now, in linear algebra, the polynomials are always written like this, starting with the smallest degree to the biggest one. So this polynomial, what are the coordinates respect to this base? Well, it's going to be just 4 times 1, right? Plus 2 times x plus 5 times x squared. So 4, 2, 5 are the coordinates in this base. So we can say that the coordinates of this polynomial is just 4, 2, 5 in the standard base. So 4 to 5 is the same that this polynomial. And that gives you a hint of the translation of everything that we are doing now to actual polynomials in Rn, right? Because this looks very much like a polynomial in Rn, but that is then the coordinates of a polynomial in the standard base of P2. Same thing in matrices. So if we have the matrix, any matrix, let's say 5, 1, minus 1, 0. So what are the coordinates in the standard bases? So this is matrices 2 by 2. So the standard bases are going to be 4 matrices, right? 1, 0, 0, 0, etc. Well, the coordinates are going to be 5 times this plus 1 times this minus 1 times this, and plus 0 times the last one, right? Because we have a 0 here. Okay, so then the components, let me add this. So we have the complete components here. So the components of this matrix, the coordinates of this matrix are going to be then 5, 1, minus 1, 0. These are the coordinates in the standard basis. So when we see a vector in R3, or when we see a polynomial in P2, or when we see a matrix in M22, so we see right away the coordinates. So when we see the vector, we can see the coordinates relative to the standard base. So we can see here 3, 1, 2, we can see here 4, 2, 5, we can see here 5, 1, minus 1, 0. So we see right away the coordinates relative to the standard bases. The problem is that many times in linear algebra, we need to change bases. I mean, the basis is just an artificial system of references that we put in our practical problem in order to solve the problem in the best possible way. So sometimes the standard basis is not going to be the best basis to express your vectors. So in those cases, you may need to change the basis. And for that, we are going to change the basis. I mean, if we have the polynomial like this, express it in the standard basis, you may want to express this polynomial relative to another basis that is not this one. So this is a basis, so prove it. I mean, you can prove, as we tried a moment ago with this other set, prove that this set is actually linearly independent. So not like the previous one that was linearly dependent, this one is linearly independent. There are 3, so then it's a basis. And now suppose that we have any polynomial, let's say the polynomial 3 plus x plus 2x squared. So how do we express this polynomial in these bases? I mean, what are the coordinates of this polynomial, but now relative to these bases? We can see what are the coordinates of this polynomial in the standard basis, right? So in the standard basis, this polynomial is just 3, 1, 2, right? 3, 1, 2. So these are the coordinates of this polynomial in the standard basis. But what are the coordinates in this base? I mean, in the base B. So the idea is to find out by how much you have to multiply the polynomials in this base. So in order to get this, we will need to do some number times the first one, plus some number times the second one, plus some number times the third one. So if we find these numbers A, B, and C, these are going to be the coordinates of this vector in this base, I mean relative to this base. So in other words, A, B, C are going to be the coordinates of this polynomial in base B. And so how do we find this A, B, C? Well, we can find it, let's say, by hand, by just doing all these operations, right? I mean, just multiply here, do that. Multiply all these things here and equal this polynomial and solve the system of equations. So once that you do then all the distributed here, you get to equal coefficient to coefficient, and you will get that these have to be equal to 3. The other coefficient of x have to be equal to 1, and the coefficient of x squared have to be equal to 2. Okay, so having this system of equations, now you solve it. You solve it in any way you like, and so you will get that a is equal 0, b is equal -1, and c is equal 1. And so we got that then the coordinates of this vector in this base are going to be 0, -1, 1. So we can say that this vector that was 3, 1, 2 in standard bases is the vector 0, -1, 1 in the base B. Okay, and we are going to be considering always now ordered bases. Since we are talking about coordinates, now the order is important, right? When you say x, y, z in a vector, it's important the order, right? So you need to keep the order, so the bases are going to be always ordered now. Okay, so that is then the way to calculate the coordinates, one way to calculate the coordinates of a vector in another base. We are going to learn now that instead of doing all these operations, this would be a way to solve it by hand, let's say. There is a result, there is a theorem that will allow us to calculate a matrix that will be the matrix of change of bases. This is an important theorem, an important result, the change of bases, that is going to be, we were doing with the standard bases, but it doesn't have two. So we can change a vector that is expressed in certain base to another base. The bases can be anything. So, for instance, to change the coordinates of a vector from a base B to a new base C, I mean, suppose that you have given the vector in base B and you want it in base C. And so then we need to calculate first what is called the change of bases matrix. This is a very important matrix, have many notations. We are going to use this one because it's very graphical, this notation, because it's easy to confuse here to change from what to what. So this one will say that is from B to C. So we put an arrow indicating that is from the base B to the base C. Some people write it also just like this. Some people also write it like this, BC. There are all different ways to write the same thing. So I'm going to use this notation that will indicate that this is the changes of bases from B to C, indicated with an arrow. And so this is a matrix, the matrix of change of bases, that is going to be calculated in this way. The columns are going to be the coordinates of the vectors of B, I mean the vectors in the all bases. So you take each vector in the all bases and you are going to calculate the coordinates relative to C. So you have to write this vector in base C. So when you find these coordinates, this is going to be your first column in the matrix P, B to C. Okay, so you take each vector of B. So the vectors that we are talking about are the vectors in the all bases. So you take a vector in B, U1 for instance, and you calculate the coordinates of that vector in the new bases. I mean, you calculate, as we did a moment ago, the coordinates of the vector U in this new base, and you put this as a column. When you finish that, you take the second vector in the base, and you calculate the coordinates in the new base, and you put it in here, and so on. So that's the way to calculate then this matrix. And then, here you will put whatever vector you have in the base B, you multiply for this by this matrix, and you will find the vector in base C. So you put the vector in your all bases, you put your matrix here, calculated in this way, and the result is going to be the vector in the new bases. Let's see an example. So let's calculate in this example just the matrix P from B to C. So in order to calculate that, so we have to take, remember, it's always the vectors in the first base here, in the base B. So we need to take these vectors. So these are the vectors that we are going to work with. And now, each of these vectors, I take the first one, 1, 2, and I need first to find the coordinates of this vector in the base C, in the new base. So I want to find out what are the coordinates A, 1, 3, plus B, 1, 4. So I want to find A and B. Here I just do the operations, right? So we will set here 1, 2 is equal to A plus B, comma, 3A plus 4B. And so from here we can say that 1 is equal A plus B and 2 is equal 3A plus 4B. So we have here a system of equations. So from this system of equations we calculate the value of A and B. So we can get eliminations, for instance, here, multiplying the first one by minus 3, we get that B is equal minus 1, and then substituting we get that A is equal 2. Okay, so we find by solving this system then what are these two coordinates. So we know then that the vector 1, 2 is actually this vector, the vector 2 minus 1 in the base C. Okay, so that is what we are interested. What are the coordinates of the vector in the base C? Okay, so we are done then with the vector 1, 2. So now we have to do the same with the other vector in the base. So we have to pick the other vector, that in this case is 2, 3, and do the same. So 2, 3, how is going to be the coordinates in this one? Well, we need to find A times 1, 3, B times 1, 4. We do the same that before, and we are going to get that 2, 3 is equal to A plus B, comma, 3A plus 4B. And so from here, we get that A plus B is equal to, and 3A plus 4B is equal 3. So let's solve this system of equations. And we'll get here that A is equal 5 and B is equal minus 3. So check the solution of the system here. So these are then the coordinates of the vector 2, 3 in the new base C. So we find out then that the vector 2, 3 can be written as 5 minus 3 in the base C. Okay, so that's the first step then to calculate the matrix, to find out what are the coordinates of each of the vectors of the first base in the second base. So that is what we just did. And so once that we have these coordinates, the only thing that remains to do is to just write them as columns. So the first column is going to be 2 minus 1, and the second column is going to be 5 minus 3. And this is then the way to calculate the matrix of the change of bases. Observe that this step takes a while, right? Because it's the one that we have to calculate the coordinates of a vector in some base. But suppose that this second base, the base C, were the standard. So you see that case would be really easy, right? Because the coordinates will be just 1, 2. Will be just what they are if one of the bases is the standard. So the problem is that when that happened, so we will have the standard in here. So we normally would like to have the standard in here so we can transform any vector in a standard form in another base. So in other words, this matrix that will be easy to calculate in the standard is not really the one that we are interested in, but beta, the one will be from C to B. Fortunately, we have a relation, a formula that relates the two matrices, the changes in the two directions. So remember the multiplication of matrices that goes like the composition of functions. We read first this one. And so here we are changing from C to B and here from B to C. So at the end we are doing from C to C. So we are not changing anything. So this matrix here is the identity. So when we multiply these two matrices from B to C and from C to B, we get the identity. In other words, one is inverse of the others. And so this is an important result that tells us that if we need a matrix from C to B, we can calculate from B to C and then do the inverse. And the point is that this is useful when this matrix is easier to calculate than this. And this matrix is going to be easier to calculate when one of the matrices is the standard one. So if we need this one with the standard here, it will be much easier to calculate this because it will be just to put the columns, the vectors just as they are as columns, and then to do the inverse of the matrix. Let's do an example using the standard basis. But first, let's write down the result, even if it's the same result, just in the specific case in which one of the bases is the standard, the S. So if the matrix is the standard one, so then the matrix P is B, that is what we will need here, is actually the inverse of this other matrix. And this matrix, because we had the standard bases here, is just to put the vectors just as they are, right? Because expressing them in a standard base is just to write the coordinates just as they are. So because of that, then this gives a simplified version for in case that one of the bases is the standard. So what we need to do is to calculate the matrix P, whose columns are just the vectors in the new bases, that's it, and then calculate the inverse of this one. So let's try all this in the example that we already know the result, the example that we did at the beginning by hand. So this was the example. We calculate everything by hand. Right, so we know already that the vector in the new basis is going to be that one because we already did all these operations. But let's calculate this using our new method. Let's calculate the matrices of change of bases. Let's start. So first, according with the result, we need to calculate the matrix P, which is simple to write down the vectors of the new base as columns, just as they are. So let's do that. The first vector here is 1, 1, 2. The second vector here is -1, 0, 1. And the third vector here is 2, 1, 3. So that's P directly without having to calculate anything in any other base. Just directly writing the things as columns. And then what we need is to invert this matrix. So let's calculate the inverse by any of the methods that you know of calculated inverses. Just calculate the inverse now. And that's it. Having this matrix, the result tells us that we need to put just this matrix, put any vector that we want in a standard there, and we will get as an output the vector in the new base. So, in other words, we just have to multiply whatever vector we want to change of base, multiply by the matrix P to the -1. So in this case, the vector that we wanted to transform with is 1, right? 3, 1, 2. So let's multiply by this matrix. Three, 1, 2, because the vector that we wanted to express in the new base was the vector 3 plus x plus 2x squared, right? So this is the vector that we wanted to change the base. That's why it's 3, 1, 2. Okay, so all what we need to do then is to put the matrix P minus 1 and multiply it by the vector. That's it. So let's multiply. So this times this is going to be minus 3 half plus 5 half minus 2, minus 1. And so this times this is going to be minus 3 half minus 1 half plus 1. And this times this is going to be 3 half minus 3 half plus 1. Okay, so let's do these operations. And the result here is 5 half minus 3 half is 2 half, which is 1 minus 1, 0. And then 3 minus 1 is minus 4 half, which is minus 2 plus 1 minus 1. And so 3 half minus 3 half is 0 plus 1, 1. So these 0 minus 1, 1 are then the components in the new base, which is something that we knew already, right? So this is what we had calculated before by hand. So I used the same example, so we are sure now that this is correct. I repeat once again then the steps. If we have in a vector space given another base and we want to express a vector that is expressed in standard coordinates, right? I mean related to the standard bases. So if we want to express this vector in the new base, what do we need to do? Well, first we need to calculate a matrix P. This matrix is just the matrix whose columns are just the vectors of the new base. I mean, this vector, and this vector. These are what are these three columns. And once that we calculate in that way the matrix P, we calculate the inverse. We calculate the inverse by any method. Once that we have the inverse, we just multiply by whatever vector we want to express in the new base. And the result of the multiplication will be the vector in the new base. Okay? So this was the vector in the base given, and this now is the vector in the new base.